So here we're continuing exercise 1930. We're going to do H, I, and J. So in these, they're asking you to make these different molecules starting with benzene. So we're going to start with just a regular old benzene ring and make each of these different molecules. Okay, the first step is just to think about what recipes you need to use in order to add those branches onto the rings. So for example, these are our possible recipes, and we just need to know which ones of those to use. Now for this bottom one here, if you're going to add an NO2 onto the ring, that's nitration. You do that by adding nitric acid and sulfuric acid. So here you would have nitric acid and sulfuric acid. For the branch on top, that is a new carbon-to-carbon bond you're forming, and so that's a sign that you're going to use the Friedel-Crafts alkylation or acylation. Friedel-Crafts alkylation is usually preferable because you don't have to reduce the carbonyl. With Friedel-Crafts acylation, you get that carbonyl there, and you just have to do another step to reduce it. So usually if you can, it's nice to do just the whole thing in one step with the Friedel-Crafts alkylation, but you have to worry about carbocation rearrangements there. In this case, though, the carbocation would not rearrange. To think of the reagent you need, draw a box around that carbon chain, redraw the carbon chain, and instead of the bond going to benzene, have it going to a leaving group, chlorine. And then the carbocation you would get, the chlorine leaves, and you'd form that where the chlorine was. Now that carbocation is secondary. It's bonded to 2 other carbons. If it were next door at neither of these positions, it would be primary, bonded to only 1 other carbon. And so it's not going to rearrange because it's most stable where it already is. So because you don't get any carbocation rearrangements, you can do a Friedel-Crafts alkylation. You have your alkyl halide based on the branch that you have, and then AlCl3 being used as a catalyst. So those are our two sort of recipes that we need to use. Now let's think about the order we need to use them in. These 2 branches are ortho to each other. This top branch is an alkyl group, so it's weakly activating and ortho-para-directing. The branch at the bottom, the nitro group, that is a strong deactivator. And, like all strong deactivators, it is meta-directing. So, because these 2 branches are ortho-para, we need to put the ortho-para-directing branch on first. So we have to do the Friedel-Crafts alkylation first. So we'll take benzene. It's always our starting material in this exercise. We'll treat it with our alkyl halide and the catalyst. That puts the alkyl branch onto the ring, and now we can do the nitration, HNO3 and H2SO4. And because the alkyl group is ortho-para-directing, we'll still get 2 products. But one of the products will be the one we want. So we have this isopropyl benzene, and if you do the nitration, you end up putting the nitro group on the benzene. You both put it on the ortho position, and also, actually, you can put it on the para position and the ortho position, because this branch is an ortho-para-director. So the ortho position is the one we want, and so we made the molecule we want. We would just have to separate it from the para product using chromatography or distillation. And so that's an order that gives you that a correct order that gives you that product. Okay, process is going to be really similar for this next one. First step is just to think of how we could get these branches on the ring, and then we'll worry about the order that we'll put them on the ring. So the way you get a chlorine on the ring, it's very similar to bromination. It's called chlorination. You use Cl2 and AlCl3. Next, we have an alkyl group. Now, an alkyl group, that means Friedel-Crafts, but it could either be Friedel-Crafts alkylation or Friedel-Crafts acylation. And if you first look at this, think about the alkyl halide you would need. Let's think of whether we even can use Friedel-Crafts alkylation. If we had Friedel-Crafts alkylation, we'd have that same thing, but instead of the bond going to benzene, it would be going to a chlorine. And when it turns into an awesome electrophile, wherever that chlorine is, that's where the carbocation would form. But notice that that is a primary carbocation. This carbon is bonded to just one other carbon. Right next door to it, the carbon is secondary, and so this carbocation would be more stable if it rearranged, and it does. It would rearrange there. So you'd end up adding an isopropyl group instead of just this regular propyl group. The benzene ring would end up attacking at that middle carbon, and you'd end up having that attached there. So you'd have the isopropyl group, not the propyl group that you want. So we can't do a Friedel-Crafts alkylation. We would have a carbocation rearrangement. So instead, we can do a Friedel-Crafts acylation and then just reduce it. So we'll use this same branch, but instead of going to the benzene, it'll be going to a chlorine. We'll just have the acyl group there instead, AlCl3. That's the first step, and then the second step is this reduction. So we use a zinc-mercury amalgam, HCl, and heat. All right, so that's how we can add those branches. Now let's think about the order we want to add them in. These branches are meta to each other. They're 1-3 away from each other. So they're meta to each other, and if we think about the chlorine is a weak deactivator, and it's an orthopara director. And if we think about the alkyl group, it's a weak activator and an orthopara director. So if you don't know why I'm saying that these are orthopara directors, I would encourage you to go back to the video for exercise 1919 and before, where we discuss how we can find those out. So these are both orthopara directors, but we need it meta. So it seems like we're at an impasse. How could we make this happen? Well, remember that we only get this alkyl group after we do the reduction. What do we get after we just do this first step? Let's think about it. We have the benzene ring. Oops. The benzene ring, if we treat it with our acyl halide and AlCl3, that would just add onto the ring. And notice what we have now. We have a pi bond on the benzylic position to an electronegative atom. It's conjugated with the ring. That is a moderate deactivator and a meta director. Well, we need these to add meta. So now that we have this meta director, we could add the chlorine. The chlorine will be meta. And then we can just do the reduction. So we can treat that with the zinc-mercury amalgam, HCl, and heat. And so we would end up having that same molecule but without the acyl group. And that is exactly what we wanted. So this whole synthesis is a valid way of making that molecule from these recipes. It's a synthesis for, a valid synthesis for making that polysubstituted benzene. All right, one more of these. This one is actually very similar to the last one. We already discussed how we can't, how we're making a new carbon-to-carbon bond here. Notice this branch is the same as this one up here. We're making a new carbon-to-carbon bond, so it's Friedel-Crafts, but this would give rise to a carbocation rearrangement like we saw in the previous exercise. So this is going to have to be a Friedel-Crafts acylation, and that's true for both of these. These are both the same type of branch. So for both of these, we'll have that, think of that branch, instead of going to the benzene ring, have it going to a chlorine and then the acyl group. That with AlCl3, and then we just reduce it. So that's the first step. Second step, we can use that zinc-mercury amalgam with HCl and heat. And that's the same way we would make this here. They're both the same branch. So those are all the ingredients we need. Now let's think about the order that we'd have to do those in. Let's clean this up a little bit. So now let's think about the order that we'd have to react, order we'd have to add those in. Well, notice that these are para to each other. And each of these are alkyl groups, which are ortho-para directors. So it doesn't matter the order we put them in, we'll just do it twice. We'll take benzene, we'll add the acyl halide with the metal catalyst. That will put one of these acyl groups on. We'll reduce it. Notice that we can't add another one of these because then it would add meta. This is a moderate deactivator, pi bond to an electronegative atom on the benzylic position, and a meta director. So first we have to reduce it. So now we'd have our weak activator, and then we can go through the process again. So we add that same acyl halide with the metal catalyst. Now that will technically give us two products. It will give us an ortho product, which we don't really want, and it'll give us a para product, which we do want. Oops. So we'll leave the ortho product to the side. In the laboratory, we'd have to separate those through chromatography or distillation, but then we could just reduce them once we've separated them. And we would have this same product, same molecule, but without the acyl group. And that's the molecule we want. So this synthesis here would be a valid synthesis for that, for creating that disubstituted benzene ring. So the process for all of these was kind of the same for this whole long reaction, this whole long exercise. The first step was to look at the branches and see what recipes you'd have to use to put those branches on the ring, noting that sometimes you have to use two steps to get a branch there. Once you knew the recipes you had to use, you had to think about the orders, the order you'd have to do the reactions in order to get the branches either meta to each other or ortho or para to each other. So you had to think of the directing effects of each of the branches. And that's the whole analysis for doing these synthesis problems.